All right, everyone, we're going to get started. The word on the street is that there's still lots of people chit-chatting from a good networking lunchtime. So expect people to be coming in and maybe having to fill in seats around you. So we'll be mostly kind to people coming. Oh, it's Silvana. She can be as late as she wants. So we'll be mostly kind to people coming in. A little glare now and again would be good. You can haze people if they come in late. So we have, I'm Michelle Crimmy from Clarkson University. I'm the Vice President for Research and Innovation, but more relevant to this session, I'm a PFAS researcher and I work on destructive technologies for treating PFAS. I'm not presenting today, but I do have the honor of introducing our presenters today. I have promised many folks in the audience compelling, fun, exciting presentations, and I'm sure they will deliver on that, right? There are 3 presentations, which means we have lots of time for discussion. So we're going to have our first presenter present his talk, and then we'll take Q&A. And then we'll have the second 2 presenters. I'll introduce them separately, but we'll hold the questions for those 2 and they'll address questions together. Sound good? All right, so I'm going to start by introducing Zach Pierce, who's an environmental engineer with Alonia. He joined Alonia in 2022. He focused on deploying and optimizing patented surface active foam fractionation solutions for PFAS-impacted water. Are you going to do I want to know who's heard of foam fractionation. That was going to be my first question. Nope, don't let me steal the thunder. Okay. So Zach's role at Alonia has ranged from hands-on system optimization and testing to project management for several exciting Department of Defense and private industry pilot programs. Say that 10 times fast. Exploring new applications for foam fractionation. He holds a BS and MS in environmental engineering from Northeastern University. Zach.
Thanks, Michelle. Okay, hey everybody. So again, like we said, we're going to be presenting today, starting with surface active foam fractionation. So you're going to see throughout this session today, we'll talk first about taking low concentration, high volume PFAS impacted water, and then we're going to kind of transition into thinking about how we turn that into a low volume, high concentration matrix that's suitable for disposal or destruction options. So specifically, my presentation is going to focus on one technology that's used for ex situ PFAS treatment. That technology is called foam fractionation. So who in the audience is familiar with foam fractionation or has heard of it at least? Okay, most of us have heard of it. How many of us feel like very confident in how much we know about foam fractionation? You're very familiar. Okay, at least one. Yes, good one. Perfect. So first we'll start with going into kind of broad scale how it works, what it means to actually implement foam fractionation from a process perspective. And then we'll talk in a little bit more technical detail about some data in terms of what you might expect coming out of a system, optimization and cost optimization and things like that. Okay, so first off, what it is and how it works. So foam fractionation is a PFAS remediation technology or water treatment technology. You can think of it as an alternative technology to maybe more conventional solid waste or adsorbent media-based systems such as activated carbon or resin-based systems. We also see now more commonly some reverse osmosis and membrane type systems being used for PFAS treatment. Each of these creates a waste product. The difference with foam fractionation is that the waste product is a low volume, high concentration liquid waste. So as opposed to an adsorbent carbon or resin-based system where you have a solid waste that requires regeneration or disposal, in our case, we're creating a low volume of liquid waste with virtually no solid waste. The way this works is the same as those other systems in terms of we're still trying to adsorb PFAS to something, but instead of using adsorbent sites on a coal-based carbon or something like that, we are going to temporarily adsorb them to the air-water interface of a bubble. So by injecting many, many small bubbles into a water column, we can take advantage of the surfactant properties of PFAS. So here you see PFAS molecules, and these black and green chains here are the carbon fluorine chains that are kind of the hallmark of the PFAS molecules, and then those functional head groups. So the long, especially the longer carbon fluorine chains in the PFAS molecules are all hydrophobic and tend to orient into the air side of the air-water interface of these bubbles, whereas the functional head groups, so these are your sulfonates or Other acid head groups that might be at the end of common PFAAs are going to orient towards the water side of those air-water interfaces. As we rise the bubbles to the top of each of these fractionation vessels, which I'll show you, we are separating them in a foam matrix, removing the foam, condensing that into water, and that's kind of the overview of the process. Now, specifically for this presentation, we're going to be talking about some commercial applications of foam fractionation, specifically using these three kind of containerized systems. So this gives you a sense of the scale of where we're operating. So this is, full scale operated at landfills. Today we're focusing on talking about landfill leachate. Could be at other sites. We're typically operating at, 10, 20, 100, or several hundred GPM. Okay, and that might include multiple containerized system, or it might include something developed out of the box. But the case studies that we'll talk about later today are mostly focused around using these kind of containerized systems. So we're looking at like 40-foot shipping containers up to 100 GPM, or more commonly, maybe around 50 to 70 GPM, which would be pretty common for a lot of private or municipal landfills. Now, getting into a little bit more about what's in the box, right? So I talked about the foam fractionation process, how we're introducing air. What we have here is a batch-wise process with 4 primary fractionation vessels in parallel. So when I say primary fractionation, what I mean is the untreated water coming in from your site, so PFAS-impacted water, entering each of these 4 batch vessels in sequence, parallel sequence. They're going to operate under a fixed set of parameters where we're varying the amount of air that we're adding, we're varying the fill level in the vessel. We might also be using some sort of additive or co-surfactant to help bind the PFAS to the bubbles, or some other additives such as, maybe water chemistry adjustments to optimize the performance, reduce scaling, things like that are all, common options that might be applied in these sort of treatment trains. It's going to undergo that batch process and then discharge treated water. Now, from that first process, remember, we're generating a foam waste. So maybe 5, 10, 20% of that initial volume is going to be a primary foam fractionate or foam concentrate waste. And that primary waste product from this step undergoes iterative sequences of further fractionation. So we're repeating the foam fractionation process, this time under different geometry and using vacuum, applied vacuum, to try and create a tall foam column. We almost think about this like a dewatering step. So we're going to create, instead of the primary foam fractionate from this first process where we're making a lot of waste, here in the secondary and tertiary steps of foam concentration, we want to make as little waste as possible. And I'll talk about why that's so important and how that ties into our next presentations from Revive. Okay, so finishing out these final waste concentration processes, we have a low volume, high concentration waste per destruction. Again, this is kind of a containerized water treatment plant, so that includes control room, telemetry, all of the air is routed through air emissions control, and all the storage tanks you need are on board. So we typically deploy these for pilot systems and full-scale installations at landfills, commercial facilities, or remediation sites. Just walking through this in a little bit more detail, you can see a picture of the control room here. So again, this is where our on-site operator would make changes to the aeration settings, things like that. Batch times. Water is coming in through a holding tank here, so we have essentially one equalization holding tank. One great thing about foam fractionation compared to some of those other technologies we referred to is that it's not very picky with respect to pretreatment. So we don't need to worry about things like high concentrations of TOC, TDS, TSS, almost all of that, and we've even run just straight landfill leachate with no pretreatment whatsoever, straight through the foam fractionation process. Now that water foams naturally because of all of the other co-contaminants in the water, not usually the PFAS, but tends to be TOC and a cocktail of other chemistries that contribute to foaming in landfill leachate specifically. So part of the cost benefit, which I'll talk about more in a minute, is avoiding pretreatment costs associated with carbon or resin-based systems, which might not work very well with a really high-strength complex matrix like landfill leachate. Now, again, primary treatment, so we showed those 4 batches. Here you can see in a little better detail, keeps clicking ahead. You can see in a little better detail where we're introducing air at the bottom through these venturis. So rather than using an air diffuser or something like that, we are pumping water continuously, small orifice, injecting air, and creating very small bubbles. So we're trying to maximize, to some extent, the amount of surface area of the bubbles. That's more important than air volume, which you might be more familiar to thinking about if you've ever worked with technologies such as air strippers. Again, treated water discharge from this stage. And then this step, you can see this nice picture here showing that foam column I mentioned, right? So here we're creating a tall column of foam, extracting just the driest foam from the top, gradually using vacuum. And then the bulk liquid from this step is recycled back to primary fractionation for further treatment. The waste product from that is then sent to destruction, which will be the focus of the second half of this talk. So this kind of gives you a sense of what the volume reduction is from each component of that. So on a grand scale, and it depends widely on the site and the unique characteristics of each water we're trying to treat. But each stage might reduce just 5 to 20 times from the primary stage. So this time we're still making a lot of foam from that first stage. And then the secondary and tertiary are really more focused on volume reduction, right? So we see, again, another multiple of 100 to 1,000 or more in those later stages. So for many sites, if we get a total 1,000 times concentration factor for leachate, that would be pretty typical. That's normal for some of our commercial installations. That would be for every 1,000,000 gallons you treat, for example, you would generate 1,000 gallons or less of liquid waste and no solid waste. So again, this presentation is mostly focused on landfill leachate. However, the system also works, or this technology also works for other types of water. The key is just how is that water going to foam? And so how much a water might foam has a very, very significant impact on how much waste you're going to generate. So that's what this slide is starting to get at, is for waters that foam a lot, we make more waste. Makes sense. For waters that don't foam very much, think maybe a groundwater, drinking water type application, we're going to be able to make a lot less waste by virtue of having very low foaming and very dry foaming. So we can really extract a lot of PFAS without carrying over too much water with it. Here you see a little bit more what the foam actually looks like in action. So this is primary fractionation foaming to start from a landfill. You can see this foam kind of coming up. So it's coming up through the primary fractionation vessel, spilling over a little spillover weir, and that foam is then being pushed out by air and collapsing into a tank, forming liquid. Here's an example of the end of that process. So this is after we've spent everything in the water that foams, and now we're essentially just pushing bubbly water up off the top. And then here's an idea of what the secondary fractionation foam looks like. So you can tell, compared to that previous foam that seemed much more wet, it was kind of sinking down and moving more by gravity. In this last video, you see it being sucked up by vacuum. And you have this very tall, dry foam column, which doesn't carry as much water with the PFAS. So why do we use foam fractionation in the first place? It's not that we're removing, let's keep skipping ahead, sorry. It's not that we're removing necessarily more PFAS than other technologies that have existed for a while and are common in these applications, such as the carbon or resin, like I talked about. The primary reason that many people are considering foam fractionation is because you can remove the same amount of PFAS, perhaps, as those technologies for a lower life cycle cost. So specifically, this is really important when we're talking about landfill leachate, water that is famous for having many, many, many co-contaminants. So typically, most landfills might be sending their leachate to municipal wastewater treatment plant, not commonly doing whole-scale, water treatment on site. They might be treating for a couple things. Maybe they're treating for, they have nitrate limits. Maybe they have some solids or some metals they have to handle before it goes to the wastewater treatment plant. Now, a lot of times we're saying, well, you need to treat the PFAS before it goes to the wastewater treatment plant because we don't want to treat for PFAS at the MGD scale at the centralized facility when the vast majority of PFAS mass coming into that facility is coming from the landfills. So using this targeted technology that is not going to remove all of the or be inhibited by all the other organics, solids, metals, co-contaminants in the leachate is really important. Whereas if we were using a resin or a carbon, we would need to do so much treatment, pre-treatment to get to the PFAS that it becomes much less cost effective. So that's what this figure is showing. The primary reason that we're talking about foam fractionation is because this green line, cumulative cost, is going to be lower when your media change out frequency or annual media treatment costs, including pre-treatment, are higher. And so landfill leachate is typically going to look more like this line, and then this line that's more that's cheaper or less costly than the foam fractionation might be a drinking water type scenario where you have low PFAS mass and low incidence of co-contaminants. So getting a little bit more into the field deployment, and we'll talk about case studies now and a couple of examples. We've been doing this for a number of years now. There's over 45 units deployed globally with over 25 in North America. So we've done this in all sorts of different waters and have really kind of a wealth of experience that's getting pretty robust now with using foam fractionation in just about every conceivable way. What's cool about this as well, kind of building out some more modular systems, and we're exploring different ways to kind of target specific flow regimes or target specific applications. Even now looking at semiconductor industry is one that also has quite a bit of PFAS wastewater that needs to be treated. So different applications requiring different solutions as well as different flow schemes. So just kind of mapping, looking at what that looks like. You will notice some of the kind of overall trends with where we're operating foam fractionation systems tend to correspond with where state regulations might be more stringent. So the Northeast is certainly one area where we have a lot of activity, a lot of interest in foam fractionation from the consulting and regulatory communities, as well as the government. Midwest as well, especially Michigan and Minnesota, and a little bit more even in the Southeast or kind of central Atlantic regions as well, and of course California and Oregon. Okay, so a couple case studies now. So we're getting back now to kind of the beginning of when I started. This is the first project that I worked on when I started here. So getting a little bit more into the landfill leachate and thinking about how these kind of facilities operate. Again, this is a landfill leachate. They're trucking all of their leachate on site. The problem they have is that the person who is receiving their leachate for further treatment at a centralized facility doesn't want any PFAS in it, or at least they don't want any PFAS in it that is above regulatory limits for the state that they're operating in. So what we want to do is use foam fractionation as a selective treatment technology. It's only going to remove the PFAS, and it's not going to have a very significant effect on basically any other component of the water chemistry. So they don't need to do any other alteration to any other processes. They don't need to do any, coordination or any sort of issues that might affect downstream treatment or handling of the leachate. They're just going to insert this blue box in their process, apply the foam fractionation, and then they have to figure out what to do with the liquid waste that's generated from that process. They're going to handle the effluent from our process the exact same way that they were previously. So for this pilot, we operated for about 8 weeks and planned to operate for 8 weeks, wrapped up a little bit quickly because we met the objective. So here you're seeing just regulated PFAS for that state. So this should be pretty consistent with what you might be familiar with from the New York kind of more local regulations, including HPA, NA, DA, to your commonly seen PFOA, PFHXS, and PFOS. This is a pretty common concentration scheme for leachate. I would say this is a little bit on the lower side of what we commonly see. A lot of times you can see, especially PFOA, well in excess of 1,000, 2,000 nanograms per liter. In this case, after optimization, we're able to remove all of these to below 20 parts per trillion, which was the objective. And in this case, actually below the reporting limit. So these are showing below, these are all showing as zeros on the kind of final concentration, below the 8 nanogram per liter reporting limit for this case. In terms of concentration factor, so that's the other big thing, right? So again, PFAS removal, that's one component, trying to meet our discharge standard. Second thing, how much are we reducing the waste volume? Because that's absolutely essential to the cost efficacy of implementing foam fractionation. And it's absolutely essential to integrating with any sort of destruction technology that's going to be a much higher per gallon treatment cost. So the more we can reduce the waste volume, the more economical some sort of PFAS mineralization or destruction technology can be. Another case study here is again showing us setting up in the foam, or sorry, in the snow here. This is me. This is kind of, again, back a few years ago in 2022, a similar scenario in the Northeast. Here we have a system being deployed for treating up to 70,000 gallons per day. And again, we see the same kind of thing. This is getting a little bit higher concentrations here, more what I'm talking about, above 1,000 nanograms per liter. And again, you see the same thing. So we have some low-level detections of PFOA and PFHPA in the effluent after optimization, but for the most part, we're removing those long-chain PFAAs to non-detect. Similar concentration factor here, greater than 600 times. So what I mean by that is for every 600 gallons treated, we're reducing the waste volume to less than 1 gallon. Okay, so those are the regulated compounds, but what about some of those other compounds? We're typically analyzing for PFAS by 40 analyte lists, sometimes even longer. Here's kind of a broader picture of detected PFAS and percent removals for that site. So here we're also including some unregulated shorter chain PFAs. So if you've heard of kind of different PFAS chemistries, you're familiar with those. Most of the compounds that we're regulating or attempting to regulate now fall into the class of what we would call long chain. PFAs, or perfluoroalkyl acids, and those would be these compounds up here. So PFOS, NaOA, HXS, HPA. And then down here, you start to have PFAS molecules that have less carbon fluorine bonds. They're shorter, and that means they're less likely to adsorb to the bubble surface. They don't have quite the same surface activity that those long chain compounds have. As a result of that, you see the performance drops significantly with essentially what their adsorption capacity or their adsorption coefficient is for the air-water interface. The PFHXA, we're removing around 50%, but then you get to these short chain, the C4, C5 carboxylic acids are very difficult to remove. In this case, only remove somewhere around 10%. Now, we also have, and we see this in quite a bit of literature as well as the field work, that adding some booster agents or other sort of surfactant chemicals can enhance the removal of PFAS. We didn't do that in this site, but in some cases we're adding cationic surfactants specifically, such that the cationic molecule that we're adding has a temporary electrostatic attraction with the PFAS molecules, which are anionic, at the bubble surface. So because those are also surfactants, they're going to be captured and form these bubbles, sit on the surface of these bubbles, rise to the surface, and their interactions with the PFAS at the bubble surface help keep the PFAS on the bubble and help prevent them from resuspending in liquid during the separation process. So in those cases, we might be able to get the removal for, PFHXA or PFBS up quite a bit. It's really difficult in landfill leachate, though. We see quite a bit of inhibition in using cationic surfactants in waters that are very high strength, TOC or other co-contaminants. Then lastly, we'll just touch briefly on system optimization. So, I showed kind of those endpoint performances in terms of what the data looks like when we leave the site, leave the system in the hands of the permanent operator. But along the way, we might be doing system optimization. A really common thing to do is just adjusting hydraulic residence time, right? So one of the easiest things we can do to improve performance is just treat the water longer. It's quite common sense. And here you see going from 20 minutes, 45 minutes, 60 minutes, and then 60 minutes plus adding the cationic surfactant that I was just talking about. So in this case, you see, the most notable improvement with the cationic surfactant, like I mentioned, is that short chain PFBS, where you see that the PFBS removal is increased with increasing the fractionation time, but only up to a point. We actually don't really see any difference between 45 and 60 minutes, or if anything, it's a little bit less for whatever reason, but adding that cationic surfactant makes a big difference for those short chain molecules. Whereas for those long chain PFAS, we see once we get the treatment time up to 45, 60 minutes, typically all the long chain PFAs are going to be removed regardless. So that's my presentation. I think we have a couple minutes for questions, and then we'll move on to the destruction piece. And again, we'll circle back at the end of this to ask questions from all three of us. So if you have a question that you want to save, you're welcome to do that as well.
Zach, as you get questions, can you
Yeah.
repeat them to benefit anyone?
Yes. Yep.
Nice presentation. Really interesting work I've seen over the last couple of years. Could you talk about that last slide where you showed the different chain lengths? Sorry, the voice one for. Can you comment on why you think 6.2 FTS is not?
Yeah. Yes, that's a good question. That's actually I almost wish I didn't put up there. This is very anomalous. This is not normal at all. So yeah, with 6.2 FTS, typically we would see a much higher removal. A lot of these sort of compounds in the class of kind of the fluorotelmer groups, you can see transformation actually happening during the foam fractionation process, which surprises a lot of people. We know there are oxidation pathways for a lot of these precursors or certain other PFAS that might break down to 6.2 FTS is, kind of an intermediate product. You see that as well with other compounds such as 8.2 and a lot of stuff if you start expanding analyte lists. This one I don't have a real explanation for. I think that you could have a situation where you're making 6.2 FTS faster than you're removing it. So essentially it's kind of, you're having transformation happen in both directions. So you have the 6 tube breaking down or being removed, because it is actually being removed and concentrated in the foam. And we do see a lot of this in foam product as well. We know we're removing it. It's not just transforming. But yeah, this one is a little bit abnormal. Leachates, you see a lot of different stuff because you see some weird stuff, especially with the FTS, the FTCAs. Yeah, go ahead first.
Question about air emissions?
Yes.
You test on that?
Yes, I'm actually giving a presentation on this topic at Battelle next month. So the very, very brief version of that is that the way air emissions, the analytical world of measuring PFAS in air is still evolving. We have some methods that have now been, more formalized, such as OTM45, which would be more applicable for these sort of compounds. However, the method of sample collection for that method is not very applicable to low flow rate or ambient air type collections. It's more developed for the purpose of stack and incinerator testing or manufacturing emissions. So we've worked with Eurofins to develop kind of something of a bespoke collection and analytical method that uses the OTM45 laboratory process, but takes advantage of kind of a modified TO13 collection method that's more suitable for ambient temperature, low flow rate, and or ambient air. So we're collecting samples around our system, inside our system, and from the emissions points, both before and after treatment. So what we know from that, just to summarize very briefly, is that you can measure PFAS in the air emissions. Mostly they transport via aerosols or droplets. They're not, typically we're not measuring with this process because it's not a destructive or thermal process. We're not measuring volatile PFAS really. We're not measuring, PFAS transformation or products of partial destruction or combustion. We're just measuring usually these kind of EPA 1633 type compounds. Most of those are transported via aerosols, which we can then capture using some sort of condensate trap and absorbent media based treatment train. The size and scale of that emissions treatment kind of depends on what you're trying to achieve, but we can get it down to basically nothing. Does that help?
So TO13, is that the stainless steel?
So we tend to be using Orbo tubes, so like resin tubes in series with like a condensate recovery step. Yeah, not vacuum canisters.
For the nice talk. So I was wondering, have you investigated, first of all, what is the size of the bubble from fractionation? Have you investigated the effect of the bubble size?
Yeah, so a bit of work has been done by that, more so at the laboratory scale. This is part of the thinking that goes into how you introduce air, whether you're using Venturis or some other method. There's some more recent work that you can kind of look into in the literature about talking about micro bubbles versus nano bubbles, essentially, if you were to categorize them. I don't have specific bubble sizes to share, but using smaller bubbles is a focus.
Is it safe to say that you mentioned the two different landfill, which I think groundwater recoveries there, is it pretty universal that more PFAS than water is foamier than lower concentrations?
Yeah, sorry, can you repeat the first part of that question again?
Yeah, is it safe to say that water with higher concentrations of PFAS in it is going to foam more?
Yes.
At lower concentrations?
Okay, so the question is whether water with higher concentrations of PFAS is more likely to foam more. Not necessarily. So there are waters that we treat where the PFAS in the water is actually what's driving the foaming, but that's not common. It's certainly not the case for landfill leachate. It can be the case in a remediation context if you have specifically unweathered, like more recent release of an AFFF type product. You're not going to see that with like a manufacturing wastewater really at all. The compounds that are really more likely to contribute to foaming are not these ones generally. They tend to be things that turn into these ones via some sort of partial oxidation process.
Let's do one more question.
One more, okay.
Now you have to pick.
Hi, Uncle.
Yes.
What used to be a national program leader for ARS, Agricultural Research Service, and there's a lot of concern at the small farm and the rural community situation. Our chat was near a military base, you had to euthanize over 6,000 head of cattle because the water, the groundwater coming from that base was contaminated. Couldn't do anything about it. Is there any movement by your company or others to take this larger system or modularize it or make it smaller so it could go into a rural community well or into a large production irrigation well where it can bubbleize the PFAS out of the incoming water? Any ideas about taking it smaller scale?
Sure. Yeah. So the question about applying the technology at a smaller scale, potentially on rural agriculture or similar situation. So yeah, as of right now, everything we've done has been an ex situ treatment that is kind of as low as 10 GPM. So that could be applicable for kind of smaller, point source situation. We do have, and we've seen kind of applications where you look at that cost model that I shared before. You might have a drinking water plant that draws from 20 wells, but only one of them has a cost curve that looks like this. So we do see a lot of situations like that where you can target different treatment trains for different portions of a total combined flow. That's one thing to think about in that sort of situation. And there is also some really interesting work being done in some of the environmental restoration programs funded by DoD, looking at in situ foam fractionation as well. That's not something that we've been working on, but with respect to kind of offsite mobilized groundwater and sites like that, that's something that's starting to be talked about a little bit.
Thank you very much, Zach.
Yep. Thanks for doing it.
All right. Next up, we have Mandy Clavin. Mandy's a project manager at Revive Environmental, where she leads customer success and project delivery for PFAS destruction solutions. She has 6 years of hands-on experience working with PFAS across multiple environmental mediums. And Mandy brings specialized depth to the emerging field of PFAS remediation. She's a licensed PE in North Carolina, has her master's environmental engineering from Syracuse and a BS environmental science systems from Lemoyne. I'll stop there, Mandy, and let you jump right in. Thank you.
Perfect. All right, yeah, thank you for that introduction, Michelle. Yep, I'm Mandy Clavin. I am a project manager with Revive Environmental. I lead customer success and project delivery for PFAS destruction solutions. As Michelle mentioned, my background's in environmental science systems from Lemoyne, and then I attended Syracuse, so I'm a proud alumna with a master's in environmental engineering. So I've been working in that PFAS space for the past 6 years or so. And so I'm excited to talk to you today about how Revive Environmental handles PFAS. So I am going to be walking us through 3 main things today. Who Revive is and the problem that we are working to solve. We're going to look at 2 of our core technologies that we use to permanently destroy PFAS, including our PFAS annihilator and our GAC renew process. And then we're going to look at some technical applications and some case study data for these processes. So the thread kind of tying all this together is that PFAS doesn't need to be managed, transferred, or stored. It can be eliminated, and we have the operational data to prove it. So starting off, who is Revive? Here's a brief look at what we do as a company. Revive is a water treatment as a service company focused on permanent PFAS destruction to reduce customer risk related to PFAS waste disposal. So the core premise of our work is that the endpoint of PFAS-laden waste is complete mineralization rather than concentration, transfer, or storage. We have several patented technologies that work to destroy PFAS, including the PFAS annihilator, which is our supercritical water oxidation based destruction technology, and GAC renew, which is our in situ carbon regeneration process. We are a technology spinout of Battelle Memorial Institute, and we are headquartered in Columbus, Ohio. In terms of markets, our work spans 4 primary areas: aqueous film forming foam, or AFFF, which are legacy firefighting foams, is a significant portion of our destruction work. Revive has partnered directly with several states on AFFF take-back programs, collecting and destroying this material. We are also in the landfill leachate space from commercial and industrial landfills. This is a rapidly growing area for us as regulations tighten on what treatment plants can accept. We also work in industrial wastewater from PFAS using and PFAS impacted operations. And we are also in the groundwater remediation space at PFAS impacted sites. So that was a brief look at what Revive does, and now here are the people getting it done. So our leadership team combines technical depth, operational expertise, and regulatory experience. On the commercial side, our president and CEO, Rick Gillespie, has more than 25 years of industry experience, and he has deployed over 1,000 projects in the US and Europe. And so leveraging the combined experience of our general counsel, our product managers, our chief technical officer, and our PFAS solutions director, Revive is able to take a novel technology from development through commercial deployment, regulatory approval, and onto customer success. All right, so now let's get into the problem that the Revive team is working to solve. One of the most important things to understand about PFAS remediation is that there's no single universal challenge. The technical requirements vary significantly depending on the source and application. So this diagram, I'm going to try to figure out the laser pointer, sorry. Oh, there we go. So this diagram provides a snapshot on how PFAS moves through the environment. So PFAS often begins in industrial spaces with airports using firefighting foams, in commercial and consumer products, and then also in agricultural applications, all of which have waste streams, which then lead to the landfill. Landfills produce leachate, which contain PFAS. This then goes down to the wastewater treatment plant, which yields biosolids for land application, discharges surface water, and then also has that leachate for treatment and transport. So PFAS, if PFAS is not properly mitigated in all areas of this cycle, it can then impact us through the drinking water, food supply, and community health. So Revive operates across 4 main waste streams in this cycle: drinking water, AFFF, groundwater, and landfill leachate. Each of these has a different volume, concentration, and matrix characteristics, which is why no single technology fits all sources. This is also a main reason why Revive partners and pairs with other technologies like alone-use foam fractionation systems. So in terms of AFFF, these usually have low volume but very high PFAS concentrations, often in the parts per million. And then further variation within this waste stream exists depending on if you are dealing with the concentrate, the rinse water, or the fire water. And so then landfill leachate also has some very high volume with continuous demand and lower concentrations of PFAS, which again, lends itself to pairing with other technologies like GAC or foam frac. And then drinking water and groundwater typically have high volumes with lower PFAS concentrations, which again make it a great candidate for that waste reduction prior to treatment. So we'll come back to AFFF and landfill leachate a little later for the case studies, but the point for now is that the Revive projects work to remove PFAS at every step of this cycle, regardless of where it shows up in the pathways. All right, so now let's get into how we actually destroy PFAS. At our basis, Revive uses supercritical water oxidation, or SCWO, to destroy PFAS. So as you can see at the bottom of this graphic, we take our PFAS contaminated media and we put it into our SCWO reactor. And as we do that, it is heated and pressurized. And so if we look to this graph on the right here, we can see that as water is heated to 374 degrees Celsius and pressurized to 3,200 PSI, it approaches what is called the critical point, which is located right here. And then it enters the supercritical state, which is when water is in the supercritical state, several key changes take place. The water is no longer behaves like a conventional liquid or gas. The density drops by about 10%. Water is no longer a polar solvent, and oxygen is fully soluble. So how does this help us? Well, PFAS compounds are notoriously stable in polar environments, and they are comprised of that carbon-fluorine bond, so that's the strongest bond in organic chemistry. But while they're in this supercritical state, in full oxygen saturated environment, the activation energy required to break those bonds is overcome and the molecules can be destroyed. So let's take a closer look at what's going on inside our SCWO destruction technology, the PFAS annihilator. So the annihilator operates at 3,200 psi and 374 degrees Celsius, driving those PFAS into that supercritical state. Once in that state, controlled oxidation breaks PFAS compounds down completely. The end product is carbon dioxide, water, and inert salt. So there are no toxic byproducts and no residue that requires future treatment. As part of the process, SCWO does generate CO2, but at quantities that are so low that they are far below the de minimis standard and do not require any permitting. The annihilator's performance has been verified against the EPA's 2024 Technology Evaluation Framework and has achieved greater than 99.99% verified destruction. Each batch that goes through the annihilator is analyzed and certified, generating a traceable record for influent composition and destruction outcomes. So since that PFAS has been destroyed, this is a huge risk liability release for our customers. So now that we understand supercritical water oxidation a bit better, let's look at how it fits contextually into the landscape of innovative technologies focused on PFAS destruction. So there are 4 main technologies in this space. We have SCWO, supercritical water oxidation, hydrothermal alkaline treatment, or HALT, electrochemical oxidation, or ECO, and plasma. So when evaluating PFAS destruction technology, several criteria matter. Destruction efficiencies across the full PFAS suite, the ability to handle a wide variety of waste matrices, including concentrated and complex streams, commercial readiness, things like permitting operations, third-party verification data, and proven scale, and an operating track record long enough to give regulators and customers confidence in the technology. So SCWO is able to meet all of these criteria. It has over 20 years of operational history in related applications and is fully commercial and permitted today. SCWO is also able to handle a wide variety of contaminated matrices and operates with a short residence time. And its destruction profile covers both long and short chain PFAS. But no technology is without its challenges. So in terms of SCWO, these include susceptibility to salt plugging, corrosion management at high temperatures, and readiness for solid matrices, all of which are areas that we actively engineer around. Understanding where each technology sits in terms of commercial readiness and performance profiles is useful context for evaluating PFAS destruction options more broadly. Taken together, what makes SCWO the right fit for Revive is its strength in destruction depth and matrix flexibility, which match the chemically complex liquid streams we handle most. So we've now looked at how the PFAS annihilator works and where it sits in a broader technical landscape. So now we're going to move on to Revive's second core technology, which is GAC Renew. And this technology serves to solve a different problem. So here's how it works. A facility has GAC vessels, which have been cleaning something that is PFAS impacted. And now these GAC vessels are saturated with PFAS. So we would mobilize to site, and we use an alcohol-based solvent on those spent GAC vessels to, so the solvent is then cycled through the spent GAC beds And on average, this cycling takes 24 hours, and we use about 1 gallon of solvent per 4 pounds of GAC. So the solvent removes the PFAS off the GAC, and the GAC never has to leave the vessel. So once the GAC has been successfully washed, we recollect the solvent, and the GAC is rinsed with water before it is returned to service. The spent solvent is then put through the solvent recovery system, which puts the solvent out, pulls the solvent out of the water via distillation. And this leaves us with some PFAS-impacted water, which we are then able to run through our PFAS annihilator, generating a certificate of processing, which ensures that the PFAS has been destroyed, the loop is closed, and it alleviates the customer of PFAS risk and liability. So we've got a little bit of data on, there we go, on GAC Renew's ability to remove PFAS within the GAC vessels. So using this solvent-based regeneration process, we are able to strip greater than 97% of PFAS that has been captured in the GAC. So that is seen on this chart on the right here. Blue bars are representing different PFAS, both long and short chain. And then this red one on the right here is the total across them, just above 97%. So now let's talk about what happens to that PFAS concentrate once it's recovered from, we just talked about that. Oh yeah, yep. So we just talked about the GAC, the ability to remove it from the GAC. Now we're going to talk about that concentrate and the solutions. So this data shows what happens when we take the GAC Renew solvent concentrate and we run it through our PFAS annihilator SCWO reactor. This figure on the left shows the initial PFAS concentrations in the recovered solvent. And then the figure on the right shows the percent reduction of each compound following SCWO treatment. So the results are clear. All the compounds were reduced to low parts per trillion levels, which is well below regulatory thresholds across both short and long chain PFAS. What this demonstrates is the full GAC Renew and PFAS annihilator workflow function as a seamless integrated system. We can regenerate the carbon, capture the PFAS in a liquid phase, and fully destroy it through SCWO, without any modification to the reactor and without any compromise in destruction performance, providing risk alleviation to our customers. All right, now let's take it back to a more bird's eye view of the PFAS pathways. So this slide illustrates the breadth of waste streams that our integrated system is designed to handle and close the PFAS loop for. Whether the source is rinsate or landfill leachate, industrial wastewater, PFAS in groundwater, or AFFF, all pathways lead to the same endpoint, complete destruction via the PFAS annihilator. This slide also does a good job of showing where pre-treatment technologies like foam fractionation often come in handy. And yeah, okay, so now, oh, sorry. So within some of these, there is quite a bit of complexity. Now we're going to look in this category of AFFF at some of the varieties that exist within that waste stream. So, so within AFFF, we are dealing with 3 distinct substreams. We have the concentrate, the rinsate, and then the fire and groundwater. So starting with the concentrate, the undiluted AFFF product, we have very high formulations and very high concentrations of PFAS, and there's a very diverse variety of different carbon content within these formulas as well. And then it is also estimated that there's about 15 million gallons of AFFF concentrate out there across DoD, airports, and different civil sites. And then looking to the middle, we have rinsate, which is often produced from cleaning large firefighting vehicles, which presents an entirely different challenge. Volumes are typically about 3 times the system capacity for concentrate. So PFAS concentrations are lower, but the potential use of specific rinsate agents also introduce additional chemical complexity. So Revive often leverages pre-treatment technologies like foam fractionation in these types of situations. And then on the right, we have fire, water, and groundwater. So very high volumes, low PFAS concentrations, but now layered with co-contaminants, including other hydrocarbons that need to be accounted for in the treatment design. So the SCWO system is designed to handle all 3 of these streams through the process, though the process parameters and pretreatment requirements differ meaningfully across them. So taking a closer look at another common waste stream, we have landfill leachate. Landfill leachate is one of the most challenging PFAS matrices for regulatory, from a regulatory standpoint. It's continuous, it's high volume, and it contains both short and long chain PFAS compounds. So including many of the emerging contaminants now under some regulatory scrutiny. So this data shows our verified destruction performance on landfill leachate samples. When the starting PFAS concentration is above 2,000 nanograms per liter, our system achieves greater than 99.99% destruction efficiency for both the short chain and the long chain PFAS. So this is not a selective result. This has been seen across the full spectrum of PFAS present in the sample. And then for our second case study, here's a look at some AFFF, specifically Ansilite 6%, which is a legacy foam that's formulated widely across military and aviation applications. So again, the data speaks clearly. Starting concentrations above 1,000 nanograms per liter, we achieve greater than 99.99% destruction of efficiency across both short and long chain PFAS. And AFFF formulations are among the most chemically complex PFAS waste streams that we see. They contain dozens of unique compounds, including short chain variants that have historically been resistant to other destruction methods. And the destruction efficiency data shown here covers the full range. So to close out, I wanted to summarize some key technical attributes of SCWO as a destruction platform. Starting off, it is destruction. It's not management. So SCWO achieves mineralization of both short and long-chain PFAS compounds, which eliminates the material rather than concentrating or transferring it. It also has regulatory compatibility. The system is designed to meet current discharge permit thresholds and performance headroom, and has performance headroom to accommodate anticipated tightening of regulatory limits. We're also compatible with upstream technologies. SCWO operates effectively alongside upstream concentration technologies such as foam fractionation, and organic co-contaminants in the waste stream do not inhibit the oxidation process. And as I touched on before, waste is very minimal. PFAS is mineralized, not moved, and the byproducts are water, inert salts, and CO2. And we are a permitted operation. Revive currently operates 2 permitted destruction facilities, and we are at commercial scale. So the technology is operating at full commercial scale, processing multiple influent waste stream types across sites in the United States. So to bring it all back together, Revive exists to permanently destroy PFAS, not to manage it, which is a serious value for our customers. The PFAS annihilator uses supercritical water oxidation to achieve greater than 99.99% destruction across both short and long chain compounds, which has been verified against EPA's 2024 framework. And then GAC Renew regenerates spent carbon in place, and the recovered feed is fed then through the PFAS annihilator, fully closing that loop. And the case data on landfill leachate and AFFF confirms that all commercial scale across different matrices is able to be successful. So that is the picture. Two technologies fully integrated, operating today with the data to back it up. And that's what I've got.
All right, and as I mentioned before, Mandy will take questions along with Eric, who I'm about to introduce right now. Eric Drugach is the Director of Sales at Revive Environmental. He drives commercial growth and deployment of PFAS destruction solutions. He has 8 years of experience in water treatment and pollution reduction and has worked with industrial clients, regulators, and environmental consultants to implement technologies for treating not only PFAS, but heavy metals and organics in water and wastewater. He has supported multiple state-led AFFF take-back programs, managing collection, transportation, and treatment logistics. Eric holds a BS in chemical engineering from the University of Pittsburgh, and take it.
All right, thank you,
from there,
Michelle.
Eric, thanks.
Okay, last but not least, we're going to tie these two presentations together that we just heard. So at the beginning of this talk, you heard about foam fractionation, which is a great technology for PFAS removal. You also heard about supercritical water oxidation, or SCWO, which is a strong technology for destruction of PFAS. Now we're going to talk about how us as Revive provides that as an integrated offering and also provides services to support those offerings. So just to kind of go through what we're going to discuss here, we're going to talk about SCWO at scale. So, Mandy mentions, what do we do with supercritical water oxidation? We're going to talk about how we're actually applying that out in the field, out in practice, and out in industry. We're going to go through how that relates to landfill leachate specifically. And I think Zach mentioned this, but we're talking about landfill leachate here. This could be applied to a host of different water sources. You could think of contaminated groundwater, industrial wastewater as being applicable here as well. Again, then we're going to start to tie these together. How do these two fit? And then we're going to share some data and case studies to wrap it up at the end. Okay, so this is a callback to Mandy's deck from earlier. Just by a show of hands, is anybody here working on a PFAS project? They've got something out in the field that they're working on. Okay, couple. All right, how about gentleman in the back? Do you think your customer or client has, say, tens of millions of dollars to spend on PFAS remediation at a site? They want to implement equipment, they want to do operation, they want to spend the whole kit and caboodle. Are they prepared to do that? Yes. Maybe not all, maybe some. Yeah, some, but maybe not everybody, right? Most of the PFAS remediation projects out there, the folks that are working on these are not necessarily prepared or want to or need to spend that type of money. A lot of these types of projects are smaller scale or they're temporary. There's a host of different reasons that they might want a service element. Instead of having to buy the equipment and actually operate this themselves, learn how to use it, implement it, build the infrastructure around it. There's value in that service component. Having a rental or a short-term option is really what's going to provide them with the ability to be successful either in the short or the long term. So this is what we're doing here at Revive. We're marrying different groups of technologies together to provide those options for customers in a variety of different fields. So whether it's, AFFF, which was mentioned earlier, it's kind of neatly packaged, high concentration PFAS sources, or it could also be, like we're going to talk about here, landfill leachate, complex water sources, areas where maybe the remote sites, there's a lot of different needs, and those end users aren't necessarily this isn't their area of expertise. They don't want to be experts in this field. They want something that's going to get them permit compliant in a cost competitive way. So again, we talked about some of the industries where this is applicable. We're not going to get into all of these here for the sake of time, but the point of this slide is really to outline that there's a host of different problems when it comes to these PFAS remediations that require different technology groups. So, starting at the left, these airports, we're talking about AFFF, a firefighting foam. Those are low volume, typically high concentration sources. They're a little bit easier to manage. But as we kind of work our way up here, you're getting more and more complex. And that could be either how the PFAS contamination is actually existing within the facility or in the environment. It could also be the water matrix that you're dealing with. And so there's a need for either variability or flexibility with that treatment program. There's also going to be a need here for somebody that's going to be able to provide that understanding and that expertise for what's appropriate. How do you apply this in a cost competitive way? So how does Revive then translate these needs into services or options for those that are afflicted with PFAS remediation? We start with GAC Renew here, which, Mandy covered earlier. So this is a technology that's really taking advantage of a tried and true way to remediate all different types of contamination, which is granular activated carbon. GAC's been around for a long time. It's well studied, and it's a way to remove PFAS. It's pretty effective. I say pretty because it has its own shortcomings, but by and large, it does a good job with PFAS removal. But the challenge can be, especially like in a landfill setting, you're also removing, in addition to PFAS, all the other stuff or contaminants that it can possibly absorb. GAC does not play favorites. It doesn't want to just take out what you want it to take out. It's going to take out everything that it can. And so if you're talking about a landfill setting where maybe they don't have the ability to, provide another treatment, or GAC is just what they have, this can be costly. This can be very service intensive, and it can be just inconvenient, quite frankly, for some of these facilities. And so this is where a technology like GAC Renew can be very valuable. You have a service component come in, somebody's going to be able to actually strip that PFAS off of the GAC, so you can reuse that material many times. I'm talking PFAS here, but you're also going to recover additional capacity. You're stripping out other contaminants as well. So you can reuse that material several times, 5, 6, 7 times. We've seen data. And again, you're not actually interrupting the process. You're taking that system offline for a period of time, but you're keeping everything there on site, and you're allowing that system to go then and operate. This is also a way for a landfill to remove some of that kind of ownership and liability of that treatment system off into a third party. So somebody else now has to manage that and is responsible for the oversight. When do we need to change out? When do we actually need to refresh that bed? So it's a way for landfill operators to really just focus in on what's critical to them, which is managing the solid waste that they're taking in. So then we also talk about here the separation and concentration components. This is what Zach referred to earlier. So we'll talk about foam fractionation a lot here in this part of the presentation as well. Again, some of this technology that was presented, this is great technology. By and large, doesn't require a huge amount of hand-holding, but there is involvement. So does every landfill want to have their own staff actually going out to a part of the landfill or wherever it is on the property, managing that asset and actually touching it, turning valves, paying attention, making sure that it's operating properly? Some can, some want to, but not everybody does. So that's where somebody like Revive can come in and say, all right, we will help manage this for you. We're going to talk about a case study here where we've done that here in a second, and talk about how that's helps that customer both with a operational footing, but also meeting compliance. So the way that we do this, again, we're taking a lot of these services to the customer. So we have a couple of models that we work with. We do everything from all of this work on site to all of this work off site. So when I say work, what do I mean? Talking about the on-site separation concentration component, so meeting that discharge compliance for the bulk water, for that bulk leachate, but then also the destruction component of that residual waste, that foamate that Zach mentioned. That can be done in a hybrid format. So it could be done on-site, could be done off-site. The model we're going to talk about here is actually the hybrid that I just mentioned. It's doing on-site concentration or removal and off-site destruction. So we'll talk about why that's an advantageous model here in a second. All right, so this slide just really paints the picture of the different scenarios that folks can find themselves in. Again, we're going to talk about foam fractionation as the primary driver and way that we're going to remove PFAS here for landfills. It's not the only solution, but that's where there's going to be a need for somebody to come in and kind of help evaluate what's most appropriate for this facility. So in the case study we're going to show, we'll talk about how we did a cost benefit analysis of some of these options, how we ended up where we did, and why we chose, foam fractionation versus some of these other alternatives. So, this is a little bit of a complex flow chart of what a landfill operator or manager is going to have to work through as they're going through meeting a potential PFAS regulation that's coming up. There's a lot of steps here, and a lot of times it's not a straight path to success. There's going to be considerations all along the way. For example, if you're talking about a water balance at your landfill, that can sometimes be a huge challenge. Like, how do I actually manage, let's say I'm opening up a new cell, a ton of new water that's coming into my operation. I might need more capacity when I go to discharge my leachate. There's many different reasons that landfills have to manage this leachate on a kind of a more close basis than maybe they had in the past. And PFAS is now becoming a part of that analysis. So we're going to get in here the case study that I mentioned. We're going to talk about what we've done here with a landfill, and we'll give some kind of background as to what we did. I like this picture because it kind of shows in plain, sight what the difference between treated leachate and untreated leachate looks like. So on the left-hand side, we've got, our leachate, that nasty trash juice that everybody loves. Kind of comes out in a funky color. And as it kind of takes its step along the process, so you go foam fractionation. All right, now you're just dealing with mostly that PFAS component, and now you destroy that PFAS. What we actually ended here with was water that met EPA drinking water compliance. Now, I might not recommend drinking it. It doesn't taste good, but that's where we can get to. That's the power of this technology and marrying these together in such a way. So why are landfills so challenging to treat or evaluate sometimes? Number one, the matrices is complex, or the matrix can be very complex when we talk about what does that chemistry profile look like. There's not just PFAS in that leachate. There's all different types of co-contaminants. You've got a lot of other organics. You've got a lot of ammonia, and everything comes out with that leachate. And it's going to be variable site to site. It's going to be variable season to season. So, in a landfill setting, if you've got a rainy season, if you're in the winter months where you're getting a lot of snow melt, you can have a very dilute leachate, much more volume. Summertime, it dries up, less volume, much more concentrated contaminants. And so that can be a tough kind of push and pull with the treatment program. So your treatment needs to be flexible so it can help be successful in all of those settings, all times of year, all flow conditions. And that gets to the other kind of component here, which are the flow conditions that we experience in landfills. Now, most landfills as they operate are relatively steady. If it's 100,000 gallon per day landfill, it's going to swing within, say, 25,000 gallons per day, roughly. Some do a little bit more, a little bit less, but, roughly speaking, they're going to be kind of consistent. But I mentioned earlier, you've got landfills that are growing. So sometimes you have facilities that are opening up new cells. And so they might double their leachate production seemingly overnight, or they might close a cell. So their leachate production might drop off, and then the chemistry could change. So you get highly variable conditions there. The other challenge we face with landfills is there's not a lot of infrastructure on these facilities, on these properties. Landfills are typically out in relatively rural areas. The sites themselves don't have a lot of building or infrastructure built on them. And so that also can be a limiting factor when we talk about how do we successfully treat or manage an upcoming regulation. So all that combines to, okay, let's say a PUTW or a county or a state now wants to implement treatment for PFAS. How do you go about and evaluate that? And this is what our customer came to see. So the case study we're going to cover here is a private landfill. This was out in the Midwest, and they had a couple of unique characteristics that made them in some ways a great fit, but also in other ways a major challenge to work through for remediation. So what made them unique? Number one, really high flow conditions. So this site can generate more than 100 million gallons per year. That's if you're doing the math there, that's a couple hundred gallons per minute at times. So for a landfill leachate, that can be a pretty high flow. And that's also a huge swing. You know, again, you're in the Midwest, you can have nasty winters. Sometimes you get a lot of snow melt, so you get a lot of volume increase. Sometimes you get none. So that was the number one challenge. How do you actually manage that water balance effectively? A couple other challenges that we saw. The site itself was somewhere where, again, there was no infrastructure, there was no building. It's not like you can just say, hey, bring in my widget 1, 2, 3, and you start running. So now all of a sudden we have PFAS treatment and we're meeting a regulation. So we had to really look at this from a ground up perspective. Now, what were the conditions that maybe made it unique in a positive way? So we had some groundwater intrusion with this landfill. So this was a site that not only had leachate, but it had groundwater blended in with the leachate. You know, Zach mentioned before that sometimes groundwater can present a much different profile when it comes to foam fractionation. In this case, it was actually beneficial. And I'll show you how beneficial it was here in a second. And then finally, this site really was concerned about, 2 PFAS, PFOS, PFOA. Now, those are tight regulations. I mean, 8 and 20 PPT respectively that's pretty tight. But again, this technology was able to meet these criteria and actually exceed them. All right, so what did we do with the landfill? So again, we have our landfill that's collecting all of this leachate into a pond or a cell. So, millions of gallons over the course of the year are collecting there. And we needed to do something to get to success, which was drop that PFAS down to 8 and 20 PPT and discharge it to the local city. And we had to get that done in a relatively short period of time. We had about 2 years, which is not a long time to go through that entire kind of build out step. So this site, we had done a pilot on using the SAF 40 that Zach presented earlier. And we said, hey, this technology really kicks butt. And what that means is we took 100 million gallons a year of leachate down to 2,000 gallons per year of waste generated. That's a huge concentration factor. So that's dropping 50, 60, 70,000 times your volume of waste that actually needs to be managed on the back end. So you're not necessarily managing 100 million gallons per year anymore. You're now managing a couple totes a month, which is much easier to kind of wrap your head around. The other way we were able to kind of, implement these SAF technologies here, which was helpful for what we do here with Revive. Remember what Mandy mentioned earlier, the SCWO system really thrives on high concentrations of organic material. It likes that spicy, like that concentrated waste, whatever it is. If it's an AFFF, it could be a leachate concentrate. So for the SCWO process and the destruction process, it improved the efficiency of what we were doing on the disposal end. So you're getting less waste generated from the landfill, and you're getting more efficient destruction on the back end. And so what that equals is a more cost-effective program overall for the customer. And so when they married those two together, that's what we did the evaluation on. And they, this site was originally looking at GAC treatment and said, hey, we're 90% of the way we think we're going to do GAC. When we came in and did this evaluation, looked at this, all of a sudden GAC wasn't as attractive anymore. Much less waste leaving the site. You're no longer hauling off media. You're hauling off a few totes a year of waste. All of that's going to be managed because the Revive approach here is to provide this as a service. So we're on site managing these assets for the customer, handling the logistics and the transportation, and then doing the actual destruction offsite at our facility in Columbus, Ohio. And so that's far less of a headache for them to worry about. And it's also, like I said, more cost effective for them long term. And again, we looked at some destruction data before, but with landfill leachate, it's really a great fit for SCWO, and the data speaks for itself. This is highly concentrated material, millions of nanograms per liter or parts per trillion of different compounds coming into the SCWO process. And on the back end, we're seeing non-detect levels, in this case, much lower than really reportable limits across the board. So we had non-detect for all of the compounds measured under the matrix. These were the top, I think it's 16 here, that were measured in terms of concentration in this particular leachate. And so the destruction was very effective. That was what allowed us to have confidence in the program to say, okay, this leachate, even over time, as maybe the chemistry changes, it's going to have a lot of flexibility on the destruction end, and it's going to be future-proof, so to speak, long-term. So I think we're getting close to time here. I do want to allow for some additional questions. So we're going to wrap up and just talk about what does this integrated offering provide for customers. Again, the number one, part to be concerned about if you're the customer, if you're the landfill operator, is the risk of evaluating, implementing, and then managing treatment. So PFAS is kind of this big, scary term. Sometimes it can be intimidating for folks to manage, or, they don't have the in-house expertise to actually do this evaluation themselves. So, when they can lean on a third party, either like a Revive or, somebody like us, it can really help to kind of put them at ease, and it can walk them through the process every step of the way. It also, puts an end to that life cycle of PFAS, because you're no longer putting maybe the leachate back into the landfill. You're not just recycling that PFAS back into the environment. It's actually being destroyed permanently. And again, when you do this kind of method properly, there's a very small amount of waste generated, both on the foam fractionation side and then on the SCWO destruction side. So it's an effective technology from a, kind of putting your green thumbprint on it. It's a, relatively low energy cost option and minimal waste generation. Again, I mentioned the flexibility before. So one of the nice parts about this integrated platform is it has the ability to push and pull. If you use foam fractionation the right way, as either, regulations change or maybe the water matrix changes a little bit, you have the ability to kind of, pull different levers, and you've got that support from the service provider to understand what's going on and help to be proactive about upcoming changes. And then, when it comes to implementing new technologies or meeting a permit, having somebody that's experienced is very valuable. Like I said, this was a 2-year cycle for us to implement this particular application. There's a lot of steps along the way that can sometimes be very new to folks. Air permitting was mentioned earlier. That's a big one. We get this question a lot. Like, what do you do with air permitting? How does that look? What does the data look like? And having the right partner to help walk through that is critically important. So again, I'm going to kind of leave us some more time here for questions, but really the take home here is, number one, the foam fractionation technology in the front end is a great way to get low cost removal of PFAS and meet a compliance point because of the way that they operate. That technology group is really growing, especially in the landfill leachate space, because of its ability to just focus on that PFAS compound or compounds, not try to go after some of those other other contaminants like other technologies will, like GAC, RO, et cetera. And then pairing that with the right destruction or disposal technology like, supercritical water oxidation, provides that customer or that, end user with end of life, responsible PFAS management long-term. Okay, I think we do have about 8-9 minutes left for questions.
And keep in mind questions for Mandy and Eric.
Yes. Yes.
Destroying PFAS, what products are you expecting? And do you have a mass balance of fluorinated organic and inorganic compounds? Because there's a lot of PFAS that's not in the party list.
Yeah, great question. So the question was, what does the destruction process actually mean? Like, what does it mean to do destruction? And then what are the byproducts? And then have we done a fluorine mass balance? So a lot in that question, I'll unpack it piece by piece. When we say destruction, we actually mean the breaking of those bonds. So carbon fluorine bonds that are broken. We're overcoming that energy barrier and we're mineralizing out the back end. So this is a bit technical, but when you talk about destruction, there's different levels of this. The highest level is actually mineralization. So it's breaking those bonds and then capturing those fluorine ions with something like sodium to create salts which are then inert and you can dispose of responsibly. So that's what we mean when we say destruction. So every time we do a destruction run, we're meeting an EPA drinking water standard effluent that we then take and discharge to our local city. The second part was the fluorine mass balance, like how do we actually navigate that part? Because again, we're using 1633 here as a basis, but that's not all the PFAS that exist. So as a rule, because we're a commercial company, we do what we, really our customers ask for. So most of our customers want 1633 as a basis. However, we do have data and we've had third parties do studies on actual organic, inorganic fluorine and doing that mass balance from start to finish. So if you're interested in that, see me after, we can share some white papers on that. Yes.
So you emphasize how this technology is very specific to PFAS, and given that the water is often given secondary treatment at another location, I can understand that. I have some experience looking at co-occurrence of pharmaceuticals and PFAS, specifically in source water for drinking water. Do you have any case studies where you had, for example, multiple, because if this one is mostly just targeted at PFAS, then would you also need, say, GAC, if you're then also concerned about, say, pharmaceuticals? Like, how do these technologies interplay in a complex matrix that is not getting secondarily treated off-site?
Yeah, so question was, how do we handle maybe non-PFAS contaminants like pharmaceutical byproducts or waste? So I'll speak to the destruction, and Zach, I don't know if you want to speak to the foam frac point. From a destruction perspective, the SCWO process will destroy any organic component. So we actually internally refer to it as the organics annihilator. It's not just PFAS. So if it's an organic contaminant, whatever goes through that system, it's going to undergo that same oxidation process. And then Zach, I don't know, foam fractionation.
Yeah, we haven't done any studies really with foam fractionation for pharmaceuticals or pharmaceutical byproduct removal. That said, there are a lot of surface active compounds that are generally proteins or kind of related to proteins that could be involved in certain either pharmaceutical products or many other just like consumer use products, cosmetics and things like that as well that have high incidence in wastewater.
Thank you.
Yeah. I think we still have a little time. Any other questions? Yes.
I'm interested in the shorter chain destruction. So from what I saw earlier, the foam fractionation is not able to capture quite as much of those compounds. Is there anything that you can do to improve that?
You want to take the capture point, Zach?
Yeah, so from the foam fractionation perspective, the main thing we do to address the short chain removal is the addition of the cationic surfactants that I had mentioned. So specifically with respect to like the main one that we look at, because most commonly tends to fall on the regulated list, would be PFPS, PFHXA in some cases as well. Those two compounds in cleaner matrices where there's less interference with the kind of interaction with the cationic surfactant, we can remove up to 100%. In landfills, it's much more difficult. You tend to see with the surfactant that removal tends to be between 50 to 90% maybe. Generally, right now we only have one full-time operation that uses cationic surfactants. The vast majority of our operations do not, and the reason for that is that there's not strong regulatory requirements for the short chain removal for most of those sites.
Secondly, follow-up is, have you folks looked at industrial wastewater at all?
We have, yes. Context to that being?
We have, for example, Micron setting up shop in Clare, but any semiconductor manufacturing wastewater.
Yeah, so question was, are we looking at semiconductor and similar industries and that type of wastewater? So the answer is yes. There's not as much work done in that industry versus some others like landfills, and it's purely just out of the need for regulation or the regulations that exist. So that industry is getting there, but they're a little bit behind some of these others that are already being regulated.
Answer for us is yes.
Yeah. Yes.
Well, thank you for the presentation. It was very interesting. But I was wondering about process from the life cycle analysis in terms of energy, both for creating the environment for supercritical water. And from your talk, I thought that perhaps you had to bring the waste all to your central facilities, so that would involve some transportation costs. And how does that add up when you look at the?
Yeah. So question was, how do we look at energy usage in the life cycle analysis for these projects? So critically, and that's a good point, right, is transportation is a big pivot when it comes to especially something like landfill leachate, talking about tens of thousands, sometimes more generated per day. If you have to transport that offsite, then you're really like changing the equation to a different set of like success criteria, because that's going to become half or more of your total overall cost. The benefit of this technology and this, what we're bringing to the table here, is you can do the treatment of the leachate on site, so you don't have to move that. And then you just take the waste from the foam frac offsite, and that's a very small volume, relatively speaking. You're talking a couple thousand gallons per year at times, and transporting that's not going to be energy intensive or cost prohibitive. And then when it gets to the destruction process, yes, SCWO is going to require, you're talking about high temperatures, high pressures, you can't really change the chemical equation. Those bonds need a certain amount of energy to be broken, but that's why having that high concentration really benefits us, because then you don't have to spend as much energy on that, because you're only processing, maybe a couple of days per year to destroy that material.
Okay.
We have time for one more?
Yep. That's it.
Yes.
Thanks for talk. My question might be more directed to Bendy. So, you presented a bar graph of the removal of different short chain PFAS using the granular activated carbon. So, I think the removal is comparable for the short chain and long chain PFAS. That's contrary to what I've seen, like how the GAC performs or the perform for long chain and short chain. I was wondering if this is a modified GAC, or how is it able to remove short chains as well as the long chain?
Actually, I'll take that one. Yeah, so that's a really good question. It was like, all right, if we're talking about GAC regeneration, why are the short chains coming off so well versus the long chains? Because when we think about GAC treatment, usually the long chains are captured easily, short chains are not. So that's actually why the regeneration process works so well. The GAC absorbs those longer chains because there's more surface area on the molecule to do the absorption, whereas the shorter chains don't have as much. So they don't like to stick to GAC as well. That's why the performance on short chains isn't as strong. And that's also why we can take them off so easily.
The high performance was related to recovering it off of, yeah.
Exactly.
Right.
All right. Thank you.
Thank you very much. So let's do one last thing before the speaker. I think we enter a break period before the 3 o'clock sessions start. So thanks everyone for joining us.